Big welcome to all of you once again to the Valley of the Shadows of Management Science. Okay. If you don't understand something, feel free and type it in the chat and let me use that as a way to address it. We always queue. A queue is a line. A line is a sequence of people, a sequence of things, a sequence of items awaiting their turn to be served. And that is something that is connected to money. You see, sometimes when there's a lot of queues, money can be lost because people become impatient. So there is this whole concept of the queuing model that is used to study waiting lines to address issues related to it. Look at the first picture. Isn't it funny? If you look at the first picture carefully, look at how many planes are in the air. And this man is trying to look at some of these planes, queuing to land, okay, or queuing to take off. During the time, in some countries, people queue like something. I think the people in Europe, they love queuing. And in a hospital, we tend to queue there. Can you think of another place where people queue? Type it there for me. Which are some of the places where people queue? It's not only people. Remember, planes queue, cars will queue, at a toll booth to be able to be ushered. Give me some places people will queue. Banks, very good. But why is everybody writing banks? During election, very good. Canteen, yes. Passport office, that is true. Hospital, that's to toll gate, that's to embassy. Okay. Say some, Kabi. Products in the production line, that is true. Food joints, that is true. Think about queues, which is not even for human beings. Fast food restaurant, that is true. These are, and you get some of these things. Students waiting to register, all of these. But why do you have to study queues? Because it can help you to give a quick service. Customer satisfaction can increase because of that. Managers can use it to make a decision. You can reduce, the effects to tolerable levels. You can raise income and all of that. Okay. Now, the thing about queues is this. There are three main components of queue. And please write them down. This is the most important one. The first is called arrival rate. The average arrival rate. It is a lambda. What is that? Even though we are calling it arrival rate, it is the average number of customers arriving in a particular time period. Do you remember the time when we used to talk about the Poisson distribution? Now, the arrival rate is the average number of, notice, is number of customers arriving. Number of customers arriving is not the same as the service rate. The service rate is the average number of customers not arriving, that's being served. So what is the connection between the arrival rate and the service rate? The arrival rate is not the same as the service rate. The arrival rate is not the same as the service rate. The two, the arrival rate and the service rate, make up what is known as a queuing system. So the arrival rate is the number of customers waiting. Number of customers who are waiting. Now, I have you to ask you a question. You raise your hand and tell me. Question. Which one do you think is going to be more? The arrival rate or the service rate? Which is supposed to be more? Think. Don't guess, because I asked you why you thought so. Eric, which is supposed to be more?
Doc, the arrival rate.
Why? Why?
Because the number of people arriving at the bank will be more than the number of people being served at a time.
Which one is supposed to be more?
The arrival.
Which one is supposed to be more? Let's go to Akrofi.
Dog, the arrival.
Why?
Because the arrival cannot be moderated. People can just walk in anytime. But with the service rate,
I didn't say which one is to be more. I said which one is supposed to be more. I did not say which one is more.
Oh, okay. Selena. Okay.
I think the service rate should be more.
Why?
Because to be efficient, the people
what do you mean
who
by
have
to be efficient?
If the person providing the service is serving people at a higher rate, that means that they are being efficient. So there will be a shorter queue instead of.
There will be a shorter queue. So when the service rate exceed arrival rate, that is good news because queues do not build up. So please note, the mu is supposed to be greater than the lambda in order to achieve a good service. Take note of this. This is very important. Okay, the mu is supposed to be bigger than the arrival rate, the lambda. Other than that, large queues will build up. In other words, the customers must be served faster. So for every time there is, the number of customers in the arrival rate, then the total number of customers being served must exceed those in the arrival rate so that queues don't build up. So that means that we need a lot of service because, of course, you can't have too much speedo service. Now, if you get that, let's check something here. So here you have some arriving customers. Okay, well, this man is carrying his things in there. This entire system you are seeing is called the queuing system. Take note, the queuing system. So you have this lady with a son. Okay, they are also going to be served. You have this guy there. You have this man in front. All of them are arriving customers. They are they are part of the arrival rate. But if you look down here, this man is being served by this gentleman. This lady is being served by this gentleman. They are in the service system. And sometimes we talk about those who are leaving, who have been served already and leaving. All of these make up this queuing system. However, those who are departed, we don't normally talk much about it. So we sometimes limit the queuing system to those who are arriving plus those who are being served. The queuing system is lambda plus mu. Don't forget, it's lambda plus mu. Write it down, the queuing system. We'll come back to this point pretty soon. So the waiting lines will form because things arrive at a faster rate than they can be served. And we know that that's what leads to queues building up. Most people, okay, in operations have enough server capacity to handle the customers in the long run, but not in the short run. In the long run, everybody will be served. Everyone will be served. But in the short run, that doesn't happen. So and the reason why that doesn't happen is because customers don't arrive at a constant rate. They all don't come, and then they all leave at the same time. Okay. Neither are they all served at the same time. And that is why we know that in the long run, not in the short run. So in the short run, queues will build up. We can have a single server waiting, and you can have a multiple server waiting. You can have a situation where the server is only one. You can have a situation where the server is 2 or 3 or 4. That case, the way you build the models are different from when the server is 1. Okay, and it is important to recognize that. Okay, so take note of the key thing, the arrival rate and the service rate. Now, the queuing discipline, which is one of the elements of a queuing model, the discipline simply deals with things like the order in which customers are served. The order, like first come, first serve, FIFO, last come, first serve. I mean, it's quite strange to have a last come, first serve when there is no appointment. Okay, last come, first serve. So maybe it's when the last come person is an old lady, who is struggling or a person with disability, you may serve the person first. Sometimes you do a random. Everybody is sitting down, then this one calls this one, a random service. Okay? Or by appointment, especially barbering shops. Okay? Sometimes they do by appointment. Now, the calling population simply deals with the source of the customers, whether infinite or finite. Those ones are not key. Okay? They are not too important. The arrival rate and the service rate is what are key. How are they organized? The arrival rate deals with the frequency at which customers arrive, and it follows a Poisson probability distribution. Poisson distribution. I'll show you a picture of that. The service rate doesn't follow a Poisson distribution. It follows a negative exponential distribution. Why? Because remember, the Poisson distribution, the arrival rate is increasing, but the service rate is falling. The arrival rate is increasing, but the service rate is falling. The arrival rate is increasing, the service rate is falling. So look at this. Okay? So if you look at the arrival rate, it's increasing, it's increasing, it's increasing, it's increasing. Okay? It follows a Poisson distribution. And of course, the number of the lambda will make the rate at which they arrive also increase. So if it is 8 o'clock, they'll be arriving quickly, say in a bank, or 9 o'clock, they'll be arriving quickly. Then towards 11, they start reducing. So the arrival rate increases. So that's what you see by number 5. Then when the lambda is 5, and when it's 15, the rate is very, very, very steep. Okay. Now, if you look at the arrival rate, again, when you look at all of this, they are increasing. Okay. And the rate of increasing shows that the Poisson distribution is getting, piece by piece as the number of lambdas go up. That is not the same as this, the exponential distribution of the service rate. So the service rate is reducing asymptotically to the point of 0, even though it doesn't reach the axis. Now, our purpose for today is to look at the 8 formulae in a queuing model and your capacity to calculate the 8 formulae. And let me just give you some advice, please. Write the formulae down as we go through each one of them. They are quite 8. They are quite confusing sometimes. You will get all of these formulae. However, it's nice to write them down because writing it down gives you a sense of what it is, because it increases your dopamine. As you move the pen in the book, the information are transmitted from your fingers to your brain, and your brain is able to release dopamine, oxytocin, serotonin, and endorphin. So let's look at the first formula. It's a probability. The chance that no customer is in the queuing system. Please note, I didn't say no customer is in the arrival, but in the queuing system. The queuing system is made up of what? The queuing system is made up of both customers being served plus those who are arriving. The probability that no customer is there, please write a formula. The probability that no customer is in it is given by what you see here. 1 minus lambda. So 1 minus the arrival rate divided by the service rate. The fact that you have 0 here means that no customer is in the queuing system. The next formula. And you want to write this formula very fast.
Doc, if you can go back.
There you go. So I don't tell me to go back. The moment I get to the formula, you write it faster. So the probability that no customer is in the queuing system is what you see on your screen. But what is the probability that maybe 10 customers are in the queuing system? 5 customers are in the queuing system. 6 customers are in the queuing system. Well, that is given by that. The probability that n number of customers are in the queuing system is given by this here. It is that. It is the lambda over the mu raised to the power, the number of those in the queuing system, multiplied by the probability that no customer is in the queuing system. And we know the probability that no customer is in the queuing system is this. So it's just a matter of lambda over mu to the power n multiplied by 1 minus lambda over mu. The probability, so if you are asked that find the probability that 7 customers are in the queuing system, and you know the value of lambda, and you know the value of mu, I guarantee you can find a probability that the possibility of 7 customers are in the queuing system. If you know the arrival rate and the service rate. Number 3, the average number of customers in the queuing system. Now remember, the first 2 are probabilities. Keep that in mind. The second 2 are number of customers, not probabilities, but number of customers. So we have number of customers in the queuing system. Remember, the queuing system is made up of those at arrivals plus those being served. As long as you are being served, even if you are served 2 hours, you are still being served, and so you are not part of the arrivals. Even though you've not left the entire system, you are still, even if you have not finished being served, you are still in the banking hall, for example, you are part of the system. And this is given by L. Those in the system are given by L. Remember, it's a number of customers in the system. So because it's in the system, there is no queue. There is no queue attached to the L because it's in the system. But when it is waiting or in the queue, the number of customers in the queue, not in the queuing system, but in the queue, then the formula will change. That formula is given by number 4. So number 4 tells you the number of customers in the queue or in the waiting line. Now watch the difference. The number of customers in the queue has got Q. The number of customers in the waiting line has got Q, but they all have L. Now the number of customers in the queue system is L, and it has no lambda squared, but the number of customers in the queue system, in the queue or in the waiting line, has got a lambda squared. So 2 of the formula are dealing with probability. And now 2 of the formulae are dealing with number of customers. So that makes it 4. The next 2 are dealing with time, not a customers, not a probability, but time. So the first one is the average time a customer spends in the queuing system. You see, just as we had the average number of customers in the queuing system, we now also have average time in the queuing system. Average time spent in the queuing system. That is the waiting and those being served. Now the time is dealing with W because W stands for waiting. And when the W has no Q, it means you are waiting in the queuing system. But when the W has Q, they are waiting in the waiting line. So watch a bit of the connection. 1 over this formula, okay, is great. All the formulas are great, but those that have Q attached to them are very important because they deal more with the Q. The most powerful of the formula is number 6. The average time a customer spends waiting, WQ, is critical. Is critical. Please write it down. The WQ is the arrival rate divided by the service rate into bracket the service rate minus the arrival rate. Remember, the U is always supposed to be bigger than the lambda. And that is why this value is very important. So take note. We have the time formula, there are 2. We have the customers formula, there are 2. We have the probability formula, there are 2. We are left with the last 2. And it's very simple. It's again probability, but you have to understand it in a different way. The chance, the probability that the server is busy. Now watch this. If the server is busy, it means that the server is being utilized. In other words, that server is being used by someone. In other words, the customer has to wait. It's the same thing. So the probability that the server is busy is the same as the probability that the customer has to wait. And so we call this utilization factor. Utilization factor, the chance that the customer has to wait. And you can see that the arrival rate is at the numerator, the service rate is at the denominator, because service rate is supposed to be bigger than the arrival rate. If they are equal, then the utilization rate is 100%. If they are equal, what does that mean? What does that mean? If they are equal, if the lambda is equal to the mu, what does that mean practically? Who can raise their hand and tell me? What does that mean practically? If the lambda is the same as a service rate. Juliet.
Please, that means there will be no queue at all.
That's it. You're smart, very smart. There is no queue at all. Everyone has been served. No one got to wait. Now, the next formula, the last formula, is the opposite of the utilization factor. The probability that the server is busy. So now, the probability that the server is idle now. So you guys waiting, it can be served. So it's the same as the probability that a customer can be served. Other than that, the customer got to wait. So the utilization is 100% minus the idle. And the idle is 100% minus the utilization. Keep note of these. We'll come back to them solidly. And since you've all written them down, if you haven't written them down, I hope you did. Okay? We will come back to this. But before we do that, let's go back to some basics. How do you better solve queuing problems? Well, in order to better solve queuing problems, ladies and gentlemen, please go back to the good old days of primary school. How do you convert minutes to hours? Do you remember how to convert minutes to hours? I'm going to show you something. It's very important. What we're about to do now is critical, is important. You're going to convert some minutes to hours. For example, what is 0.25 hours in minutes? 0.25 hours. How do you convert it to minutes? Raise your hand and tell me. How do you convert it to minutes? Of course, what you did before you converted it to minutes is what we are interested in. 0.25 hours. How do you bring it to minutes? How did you do it? How do you bring it to minutes?
Times 60.
Yes, Selena.
So please, I know that 60 minutes make an hour. So I just multiplied 60 by 0.25 hours to get 15
Good.
minutes.
So you get 0.25 times 60 minutes, and that will give you 15 minutes. That is how you convert 0.25 hours to minutes. Guys, pay attention. This is the basic of the deeper thing we're about to do. Now, let me ask you. Have you heard of if more, less divide? Remember those things. 10 minutes is how many hours? You can tell me. This time, 10 minutes is how many hours? How many hours? Raise your hand and tell me. Akrofi.
10 over 60.
I'm not interested in 10 over 60. 10 minutes is how many hours? Tell me that first. Then I'll ask you, how did you do it? How did you do it? What is the answer, by the way? Let me see some answers. Samuel.
No, please, it's 0.167, so like 0.17.
Good, 0.17. Very good. And you did that by dividing by 60. Dividing the 10 by 60. So guys, watch. If you are moving from hours to minutes, you multiply. If you are moving from minutes to hours, you divide. Keep that in mind. Okay. Come to give you some great exercises here before we get. 40 minutes is how many hours? 40 minutes. How many hours? 40 minutes. Raise your hand and tell me. 40 minutes. And I need answers before explanations. 40 minutes. Eric.
Dr. 0.67.
Okay, very good. 0.67. So guys, follow through, write it down, follow through, write it down. Okay, 0.6 hours is how many minutes? 0.6 hours is how many minutes? Raise your hand, raise your hand. 0.6 hours is how many minutes? You know, somebody is having his calculator. You're supposed to have your calculator. 0.6 hours, that's how many minutes? Samuel.
No, 36 minutes.
36 minutes. Good. Guys, you got to follow. Okay. Now, let me give you some quick exercise. I want you to do something for me. And again, this time I want to bring you here. Okay. I want to believe you can see my screen. Can you? Can you see my example screen?
Yes, Doc.
Okay.
Yes, please.
So now, if you look on your screen, if it takes 5 minutes to serve a customer at Papaya, how many customers are served in an hour? What question am I asking you? Am I asking you a question about a lambda, or I'm asking you a question about a mu? Who can tell me? What am I asking you to find? Raise your hand. Am I asking you a question, or type it there? Am I asking you a question about a lambda or a question about a mu? Which one? Lambda or the mu? If it takes 5 minutes to serve a customer, how many blah, 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 blah? I'm not asking you a question about the, yes, I'm asking you about the mu, mu. Mu is not mule, it's mu, mu. Okay, which is a symbol for the mean. So I'm asking you to tell me the service rate. The service rate. So who can tell me, if it takes 5 minutes to serve a customer, one customer, how many customers are served in an hour? If more or less divide. How did you do that? In other words, I want you to find mu is equal to what by what times what divided by what, Juliet?
I got 12 customers being served in an hour.
How would you have done the show working? That's more important.
So, so since 5 minutes, it serves one customer.
So you say 5
How
minutes is one customer.
a customer. So how many, I decided to ask myself, how many minutes will I get in an hour?
So how many minutes X will you get in an hour? Did you write 1 hour?
Yes, please.
No, you cannot write 1 hour. Since the first one is
okay, sorry.
Okay, let me change it. So how many minutes, it shouldn't be an hour, how many minutes, not how many minutes, how many customers are served in an hour? Okay, so you have 60 minutes is equal to how many customers? The way you started, that's why it ended like that. I've said that one customer is served every 5 minutes. That's how you should have said. How many customers are served? Okay, so what did you do from here?
So I divided the 60 by the 5.
Well, that cannot work. That is not really the mathematical principle you're supposed to use. When it's divided, you you're assuming. But what is the mathematical principle here? Eric, one word.
So
that's a cross multiplication.
So that's a mathematical principle, cross multiply. So this is now X. So you do cross multiplication, and then you get 5X equals to 60.
60, yes.
Now X can be equal to 12.
Well,
guys, know the principle. You're going to have a lot of these. It's important to understand and you know what is happening. Okay, let's move on. We're going to get more of
Doc, a quick question.
Yeah.
Yeah, if you are going by the principle of if more or less divide, or if less, more divide, then would you still have to use the cross multiplication?
it will still be the same thing. Even if you don't use a cross multiplication, it will end up the same way.
With the same answer, yes. Okay.
Oh, yeah.
I think that's what, is it Gifty?
That's what she was doing.
Juliet.
Yeah, that was the direction she was going earlier.
Then I've said I'm using more or less by principle. Or less modified principle. So the service rate that you are using here, you will always have to find it. Now watch this. If the first one is in hours, your second one must be in hours. So if you look at this, the first was rather in minutes. So now that you're going to find the second one should be in minutes, but it was rather in hours. So what you got to do now is to convert that to minutes. So you know that an hour is 60 minutes. Now they are all in minutes before you can continue. This is very important. Let's take another one. A system has one service facility. The service facility, one, can serve 10 customers every hour. The customers arrive at an average rate of 6 per hour. What are the chances that a customer has to wait? Let's break it down. Remember your formula here. What value do we have? Pick any value that you think has already been given to us. You can raise his hand and tell me what value has been given to us. Pick anything that is seen in this preamble that you believe has already been given to us before we even find out what we are looking for. What has been given to us? And please, for those of you who are checking answers there and writing your answers, I don't like it. Maybe you should privately send it to me. Okay, Teresa, like you go and check somewhere and you give me the answer, give it to me behind the scenes. That's better than putting some answers on the page, making you smarter. Okay, do it in private because I want people to think other than, getting answers here. This is work. And for you to have worked it so quickly, I'll give you another one, which is not in the book. Yes, Samuel.
Yeah, Doc. So I think mu has been given to us, which is 10 customers per hour.
Wait. So what you are saying is that mu has been given to us, which is what?
10 customers per hour.
10 customers. So it's 10 customers per hour. That's how you write it, per hour. This one was given us per hour. Oh, come on. See, now I need to meet everybody. Some people are very, very strange. So now you got to raise your hand. I need to unmute it. So let's go to the next one. So 10 customers. 10 customers per hour. Okay. So mu has been given. What else has been given? Akrofi. What else has been given?
Doc, the arrival rate.
What is it?
That is 6 customers per hour.
What symbol is that? What symbol is that?
That will be the lambda.
Okay, good. So lambda has been given, and that is 6 customers per hour. Okay. So on the basis of this, you're supposed to find what? What are you supposed to find here? What are you supposed to find? Looking at the question, the question is actually asking you to find what? Gifty. What are you finding?
So you are finding the probability that a customer can be served.
You are finding the probability that a customer can be served. What gave you the clue that you are finding the probability that a customer can be served?
So in the question, it says, what are the chances, which indicates probability that a customer has to wait.
So if a customer has to wait,
it's probability that a server is busy.
Good. If the server is busy, but you earlier on said a customer can be served, right?
No. I wanted to say a server is busy.
You now remember that he said the wrong thing.
Yes, please.
Okay, all right. So the probability that a server is busy and therefore the customer has to wait. And so you are being asked that question. Remember that you are being asked the chances that a customer has to wait, which means that you are being asked to find the utilization factor. Is that what you had in mind? Now, all of these are in hours. And you remember the formula for the utilization factor? Lambda over mu. Lambda is 6, mu is 10. They are all in hours. So it's 6 by 10. And boom, you got your answer. So that is how you got to attack this question. Utilization factor. There's going to be more of this. Let me give you another one. And again, all the formulae are coming into play before we get to the big deal. Okay. All the formulae are coming into play. So Samuel, you gave me an answer of 10 customers per hour. Arara rates, Zakia, you gave me the answer. Okay, let's go to this one. I want you to think. Think. I'll slow down here. The ticket booth at the Bravo campus is operated by one person. Okay, let me go to you. Your hand went up and is now down. Okay, let's move on. One person is operating the booth during the annual Yam Festival. Here's a question. The seller can serve an average of 15 customers per hour. So you can serve 15 customers an hour. Now watch this. The next part has changed the hour. On average, 3 customers arrive to buy tickets every 15 minutes. So minutes. So keep that in mind. Question. Determine the average time a customer or buyer must wait. Determine the average time a customer or a ticket buyer got to wait in the queue. So it's asking you of something. We'll come back to that. Okay, so Vivian, your hands have been going up consistently and you keep it down. You raise it up, you keep it down. You raise it up, you keep it down. I don't know why you do that, but could you please tell me why your hands goes up and down, goes up and down? Because normally when it happens, Vivian Koku, what is happening?
Yeah, hello, Doc.
Yes.
You are moving too fast, please. If you can slow down a little bit.
I could have easily typed that there. All right. You could type it there next time, okay?
All right, okay.
So, see, his hand has gone up again. Okay. So, the ticket booth is operated by one person. The seller can serve an average of 15 customers every hour. So watch it. If you can serve, the word serve should always give you the clue that we are talking about what? What are we talking about? It's very important you learn this. I can give you the answer, but I like it when some of you tell me. Okay, now you can put it in the group. What is the word serve always giving you the clue about? It means that you have what value? So you don't need to raise your hand. You can type it there. Okay, these are easy questions. Okay, you have the mu. Well, okay, you have the mu. Okay, so that is the mu. Now you got to check whether it's in minutes or hours. We are told that it's 15 minutes per hour. That's what we are told. 15 minutes per 15 customers per hour. So you have 15 customers per hour. But the other one is 3 customers arriving every 15 minutes. So there are 2 possibilities that we can do. We can convert this to the hours, or we can convert this to the minutes. It's always good to keep it all in minutes. So if you have 15 customers per hour, that is 15 customers every 60 minutes. So that one is done. 15 customers every 60 minutes. Okay. You have that there. Now we need the lambda. We are told that 3 customers arrived. So I know the first one was served, the next one is arrived. So that's why we know that it's a lambda. 3 customers arrive every 15 minutes. That's ours. So now you have 15 minutes every 15 customers every 60 minutes. And now we are having 3 customers. Okay. Can bring that down here. 3 customers every 15 minutes. So got to change it to 60 minutes now. So now that we have 60 minutes here, every 3 customers, you are getting 15 minutes. 15 minutes, you are serving 3 customers. 15 minutes, you are serving 3 customers. 15 minutes, you are serving 3 customers. So 60 minutes, you serve how many customers? If you use your mind to answer, you should be able to know how you completed it. Because one thing I know is that the human mind is faster. So you might use your mind to answer without knowing how you completed it. So if every 15 minutes you are serving 3 customers, then it means 60 minutes, you're going to get more customers. If more, the less value, this one, the one that you have both, the less value will divide. So the 15 must come down. Okay, so you're going to have 15 over, sorry, you're going to have 60 over 15, okay, equal to, we expect the bigger one. No, we expect this value here to be bigger. That's what you do. So that value must come. Let's call it x. So it's going to be x over the 3. That's the meaning of if more, less will go down, less will divide. And so you now cross multiply 60 by 3, which gives you 120. 15 by x is 15x. So you get 15x equal to 120. If you want x to be 120 divided by 15, and that will give you what value? And I see that you've written it beautifully there, 12. So you get a value of 12. So it means that your lambda is going to be, you're going to have 12 customers every 60 minutes. That's what you're going to have. Now, Clementine, you have a question?
Doc, not a question, but
if it's not a question, that's okay. Okay, John Plant, you have a question?
Yeah, sir. You wrote 120, it should be 180.
Okay, all right, yeah. So this value will be 180. And you divide it by 12. You divide it by 15 and you get 12. So the value for lambda is going to be 12. And that is going to be 12 customers per hour or 12 customers per system. That's what you get. Adams, you have a question? Okay, he doesn't have. All right, let's move on. The next thing to do is to now come back to the question. So you now know the values of the mu and that of the lambda. That's the most important thing. Mu and lambda must be known at all levels. Okay, so let's document that. So mu is 15 customers. Always bring the units, customers per hour. And then lambda is 12 customers per hour. The next question says, blah, 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 blah. Okay, how? The answer is done. So the question is, okay, now we go to the question. Okay. Determine the average time a buyer must wait. You see, he's asking me a question about what? Time. The time was one of the formulae that we had. The average time a customer must wait. So what formula is he asking you to? Is it L? Is it LQ? Is it W? Is it WQ? Is it U? Is it I? Which formula are you being asked? Good answer, Eben. That is unfortunately not correct. Because when you write W, you have not answered the question. It's rather WQ. Okay. So it's going to be WQ. Remember, wait. Average, didn't say determine the average time a ticket buyer will be in the queuing system, but must wait. So it's actually your WQ. So this is where you now go and pick your WQ formula. So this is your WQ formula, which is now equal to, is it 1 over lambda? Okay, I just want to be sure that you can remember it. Let me just go back here so that I can write it here for all of you. You see, even though these formulas sometimes will be given to you, it always makes sense for you to know them. Because when you know them, you are going to be able to beautifully, catch some few things related to that. So it is going to be WQ, okay, then lambda divided by mu into bracket mu minus lambda. That is a formula for the weighting. And we know the lambda already. We know the lambda to be 12. Lambda is 12. We know the mu is 15. So find the answer for me. We are going to have 12 over 15 into bracket 15 minus 12. What answer do you get? This is where you got to take your calculator and then find the correct answer. So do that, let me see. And when you are done, you see, you will get the answer in hours. Don't forget, because these were in hours. The 12 was 12 customers per hour. The mu was 15 customers per hour. So whatever answer you're going to get will be the time in hours. And if you want to get the time in minutes, you multiply it by 60. So work it out and tell me. What do you get? Let's see. I got a first answer from Bishop privately. Very good. I got a second answer from Samuel privately. So that is how you got it. If you do this, okay, you're going to get, I think you're going to get 0.22 something. 0.2267 also hours. Is that it? Yeah, I think so. So you're going to get 0.2267 or something hours. And when you multiply that by 60, you're going to get 16 minutes. 16 minutes. Take a calculator and confirm. So that is what you mean. Let me go back to the question. That is what you mean by the average time a buyer must wait to be served. It's the same as must wait to be served. That's it. Any question on that? Fantastic. Okay. Now, you can also cancel, because this is where sometimes you don't have to use the decimals. Because sometimes you use the decimals, it can destroy the way you got it. So I like to sometimes use not the decimals. When you check this, for example, okay, 3 goes into 12, goes into 12, 4. 3 goes into 15, 5, okay. 15 minus 12 is 3. 5 times 3 is 15, okay. So in principle, you're going to get 4 over 15. Now, if you want to multiply, if you want to convert that to minutes, you just multiply that by 60. You see, now it becomes easier to now see that 16, because 15 goes into 64. 4 by 4 is truly 60. So sometimes when you keep it in fractions, it helps you for some to cancel very, very nicely. Akofi, you may have a question. So you got to know how to tackle each one of this.
Look, okay, so I use per minute. And so my mu was 0.25 and the lambda was 0.2. And so if I'm calculating, would I have to leave it per minute or would I have to convert into
You always keep it in 4 decimals when you're calculating. Unless the question asks you that you should leave everything in minutes. And yes, sometimes you'll be asked to leave everything in minutes. So once it's all, leave everything in minutes, you keep it in minutes. But if not, okay, you keep it in 4 decimal places.
Okay.
All right. So we've been able to get to the first part of the question. The next part of the question is this. Let's go back and look at that. It says that determine the portion of time the seller is idle. This is very easy. You must remember the idle formula. Okay. The portion, the word portion here means what? Type it up. The word portion. Determine the portion of time. Portion is what? Percentage. Okay. So we're looking for the portion of time the seller is idle. How do you do that? It's very simple. Very, very simple. Too simple. Okay. Let's see how you can crack that. Portion of time the seller is busy is just idle here. So it's idle. And idle is a utilization 1 minus the utilization. And the utilization is actually lambda over mu. Lambda over mu. And so you just calculate 1 minus the lambda over mu. Lambda over mu, lambda was 12, mu was 15. So this is actually going to be 1 minus 12 over 15, which is 3 over 15. And that's it. Take a calculator and you find the value of that. Those of you are doing that. Sorry. Yeah, I think so. Yeah. So what do you get? That's 20%, right? I want to believe it. So you get 0.2 or 20%. So the probability that the server is idle is 20%. Let me ask you, if the probability that the server is idle is 20%, then the probability that the server is busy is what? The probability that the server is busy will be what? Because I'm coming to trick here. It's going to be 80%. Very good. Okay. So now let me ask you the next question. Look at the next question here. It says that the management of Ebrawo likes to have its workers or operators working 80% of the time. What must the service rate be in order for the operators to be as idle as management would like? Management would like them to have its operators working. Working here means utilization. So in this case, he's telling you that the utilization here is 80%, 0.8. And now he's asking you, what must the service rate be? So you need the lambda, sorry, the mu. So you just have to look for the formula for the utilization. The utilization here is given by the lambda over the mu. And he's asking you, what must the mu be, the service rate be? Well, the utilization has been given us 80%. So the utilization is 0.8. We need mu. But we know what lambda is because we know that in this story, lambda was 12. So what must, this is a very funny question because it's kind of taking you back to the same thing. What must the service rate be? Exactly. And the service rate B will be cross multiply and divide, which would now bring us back to the mu equal to what? 15. So what must the service rate be for the operators to be as idle? As idle is the same as 1 minus the utilization. And utilization is the same as 1 minus the idle. And that gives you, the service rate must be 50. So that idle will still be 20%. Utilization will be 80%. That is how you work this. So you can check it out. Okay. Let's go to the deeper one. These are the preliminaries. Okay. Let's get to the deeper one. All the things that we've gone through are here. So you can check it. Now, sometimes, and this is where I got into the deeper part, so please pay attention. Sometimes management, we're dealing with single service, single, individual. So sometimes the management would want to have several approaches to reduce the waiting time. And one way you can reduce the waiting time is when you bring more service, more service, more service. Now, when you bring more service, something is going to be affected. So let me come back here and ask you some deep thoughts. When you bring more service, what will be affected? Is it a service rate? Or is it a mu or lambda? Is it a mu? Just type it from. This one is very simple. Is it a mu or lambda? When you bring more service will affect what? Mu or lambda? Is mu. Okay, good. So it will affect the mu. What will it do to the mu? Tell me. What will it do to the mu? More service, what will that do to the mu? It will, somebody says it will reduce, it will reduce, it will reduce. What will it? Somebody says it will increase, it will increase, it will increase. You see how people think? You see how people think? Somebody says it will reduce and increase at the same time. Beautiful. What do you think more service is going to do? What will more service do? You got to know this. Okay. How is that more service? But what is it going to do? What will it do? Because we are talking about more service. So obviously, yeah, you have to watch the word, more service. So we know that more service is going to do what to the service rate? To increase the service rate. So the mu is going to go up. But what would that do to the time? You see, some of you are concluding without telling us what would that do to the mu. But what would now that do to the time, waiting time? What would that do to the kill, waiting time? It will reduce the time. Okay, to reduce the time. I will increase the mu. Okay. Now that's one way you can affect the time. Another way is when you add a new checkout counter, okay, or a new machine. So instead of getting a human being to do the service, you rather bring a machine. When you go to Tesco, okay, and other places, you got machines. When you go to the airport, you got machines that are serving, people because the machine. Now, what would that lambda? Of course, the machine will affect the lambda. Keep that in mind. Now, let me trick you here. The machine will affect the lambda. Who can tell me under what circumstance would the machine affect the lambda instead of affecting the mu, the service rate? Who can tell me under what circumstance would the machine affect the lambda? Because the thing is that if there's a queue, right? And I've seen this at the airport before, and I've done it before at the airport. It was so funny. I got to the airport, and almost 100 people are on one lane. Meanwhile, I could see clearly that there were 2 lanes. And 100 people, and I was going to be like 100 and something, 120 something. So straight away, I started walking bypass the people, because I could see that there's another lane there. And nobody is going to that lane. Now, what do you think people will do when you start walking towards that second lane? They'll start looking at you and calling you out crazy in their head, calling you out crazy. Where's this guy going? Who does he think he is? We are all in here, and he's going there. So I started walking confidently, going there. And then when I got there, the lady came forward and served me. And then I turned. What do you think I'll be seeing? I'll be seeing what? I turned whilst I had entered. And what do you think will be happening to the other queue, which is made up of over 100? Come and see. People are now leaving that lane to follow me, even though they were laughing at me. Sometimes you have to be the odd one out. Sometimes you have to be the crazy one in life. But another time, I was going to Ireland, and I did the same thing. The lady looked at me and said, hey, just go back. It doesn't always work like that, isn't it? It doesn't always work like that. But again, the key point is that you see that the queues will be reducing. The original queue, so there will be another lane. So if there was a machine that can do the service, the other people will go to that machine. And so the arrival rate, whenever you arrive, you don't go to increase the service rate, but it will increase the arrival rate. That's my point. Okay. So it will do something to the arrival rate. It will reduce the arrival rate. Those in the queue arrival section that were originally with the first guy, they will start going down because now there's another one that is serving them. And again, the timing, the waiting time will also go down. So the WQ will reduce as a result of that. The WQ will go down. So either you give more service or you increase the arrival rate. You add a service, more service, the new guy, or you add a new checker counter, and that will, affect the arrival rate. Either case, we know that two things are going to happen. Either case, WQ, which is a waiting time, will go down. We know that, but something will also happen. The time saved will increase. So you save time. So another thing that will happen is that time will be saved, which is what many people want. And then finally, there will be a monetary gain over time. Because the thing is that the company, people will start getting happier. There'll be a monetary gain. And we're going to check all of this situation in a real life story. Okay, so let's go to the slides and look at a real life story. ShopRite, Tesco, Sainsbury's, Morrison's, Argos, anything, ShopRite. Now, if you've been to ShopRite, sometimes it can be so packed. It's a busy center for residents in East Legon and other places. Okay, so you got Eric. Yes, Eric, go ahead.
Yeah, Doc, I was just checking. We don't have control in terms of the arrival rate, right? So how does...
Who are the we?
I'm saying that, so for instance, at the airport, one does not have control of the number of people who comes in.
Who do you know one does not? Who is that one does not that you're talking about?
The airline, hello, Doc.
Yeah, go ahead.
If I take
you didn't think that I will ask you that question, so you were thinking about it.
Yes, exactly.
Yeah, I know. Now you are saying that the airline yes, controls it because once they put the machine there, they are controlling it. They have control.
But it still doesn't reduce the number of people that comes.
That what?
It still doesn't.
We're not interested in the number of people that come. We are interested in the number of people queuing. A lot of people can come, but they will not queue.
Okay, clear.
Yeah.
If it's in respect of the queuing, then that's clear.
That's the essence. Because so many people come at the airport, not all of them join the queue. Some came to, leave others at the airport. Sometimes you can have a lot of people who have, they are a family of 5, and yet only one person is queuing. So it's not everybody. So we are dealing with the queues, and the queues are there. It's not the human beings, it's a queue. And remember, it's not only human beings that can queue. Sometimes bottles can queue. All right, so with that in mind, how do we now handle the situation? Assume that 2 customers arrive. This is in ShopRite. 2 customers arrive every 12 minutes. Put it down, put it down, put it down, put it down. and 3 customers are served every 15 minutes. And that currently there's only 1 cashier. Let's deal with that first. Let's deal with that first. 2 customers arrive every 12 minutes. Write it down, write it down, write it down. 3 customers are served every 15 minutes. There's only 1 cashier. What is the average waiting time? That word, waiting time, is dealing with what? What symbol? What symbol is that? What symbol is that? What symbol is that? Waiting time, waiting time, waiting time. What's that? Someone says it's confusing. It's WQ. It's confusing how the arrival rate reduces. Okay. Is that it? Okay. Waiting time, Zakia, you sent me the WQ. So it's WQ. Okay. It's WQ, waiting time. So, okay, the same question I answered. We don't control the arrival rate. All right, you got it now. So that is it. Waiting time is WQ. Let's go to document that. Okay, I just want to write it here for you guys to see it well. So the waiting time is WQ. That's what we're going to find. But we are told that the customers arrive every 12 minutes. That word arrive is lambda. How many customers arrive every? 2 customers every 12 minutes. So you have 2 customers every 12 minutes. So you have to now check how many customers arrive every hour or every 60 minutes. How many customers arrive every 60 minutes? Always convert it to minutes. So if you have 2 customers every 12 minutes, how many arrive every 60 minutes? Give me the answer. Let's deal with that first. Let's deal with that first. You have to take all of them to meet. How many? How many? How many? How many? How many? How many? You are converting it to 60. Then you can now deal with that. 10. Excellent. Good. I got some great answers here. So you're going to get X to be 10. Okay, so that is 10 customers per hour. Let's go to the mu, the service rate. Okay. The mu, we are told that 15 minutes, 3 customers are served. So 3 customers are served every 15 minutes. So how many customers are served every 60 minutes? 60 minutes, if you want to go, you write 60 minutes here. Then you find the value of X. How many is that? 12. Excellent. So you get 12 customers are served every 60 minutes, which is every hour. So you got the value of lambda and you got the value of mu. This is what you got to get first. This is the most important thing. Once you get the value of lambda wrong or mu wrong, forget it. You are dusted. And so you want to know how to do this conversion very, very quickly. Whatever you have, convert it to 60 minutes or an hour. And then once you got the value, that's what you're going to use. But you're going to use the value to calculate the waiting time because the question was explicit. Let's go back to the question. The question says that, what is the average waiting time in minutes? In minutes. Remember, what you have are customers in hours. So whatever you finish, you got to convert them to minutes before the service begins. So he's asking you to find the WQ. Okay. So how do you find the WQ? You write WQ, and this WQ is given by lambda over mu into brackets, mu minus lambda. This is your waiting time. Let's find the value. Okay, take your 12, take your 10, and then find the value. Find the value, find the value, find the value. Your colleagues are finding it. Find the value, find the value, find it, find it, find it, find some, do some. Okay, do some. So now, like I said, you normally get these things correct to 2 decimal places. Okay. So you're going to get lambda, which is 10. 10 divided by 12 into bracket 12 minus 10. 12 minus 10 is 2. 2 times 12 is 124. Okay. So you have 10 divided by 24. And that will give you a certain value. Okay. You have to do it yourself. 10 over 12 into bracket 12 minus 10. And when you do that, you are going to get whatever answer you get is in hours. So you got to multiply it by 60 to get it in minutes. I think when you do that, you're going to get in 2 decimals. Let's keep it in 2 decimals, okay, for now. 2 decimals will be 0.42. Okay, that's for 0.42 hours. And when you convert it to minutes, it will be 25.2 minutes. Is that it? Let me see. Let me see some of your answers you're getting. Okay. Now, if you get 25, it means that you are using 4 decimals. But now I just want to go by what one guy just spoke about. Okay. Let's go with 2 decimals. So everything now 2 decimals. Everything has 2 decimals. Okay. Let's keep it as simple. So 2 decimals. What are you going to use it for further work? So you're going to get 2 decimals. 2 decimals is 0.42. You're going to correct it. And you now do the value, you get that. So let's use that 0.42 and let's work with that, okay, just for simplicity's sake. So you get 25.2 minutes. That's what you get. So that's a number of minutes, the waiting time. So people, what this means is that don't keep the hours in fraction, always convert it to minutes. That's the rule. What this means is that the customers are being served and they are waiting they're waiting 25 minutes in the queue before they are served. The question is whether that is good news or bad news. Okay. You are waiting in the queue. Please, if you have a question, you ask me and I answer you, then you know that is the way it's got to be. Yeah, Eric.
No, so Doc, the reason why I ask is that if you keep the hours in fraction and you multiply by 60 minutes, you get exact 25 minutes.
Yeah, but it's not always like that, right? It's not always like that. You know that. It's coincidental. I did that before, and it confused some other people, but I'm saying that it's not always like that.
Yeah, okay.
Yes. So if you're going to set up the rule that it should be in 2 decimal places, we keep it like that, so that everybody will go. Unless you want me to set up the rule, I will keep it in fraction. But I believe me, some people will not even understand how the fraction works.
Okay, clear.
Sometimes you keep it in fraction, it will still get back to decimals. And then it causes a lot of problems. So let's keep it in 2 decimals. Okay, so now you have this value. 25 minutes is too much. To wait 25 minutes in a queue before you are served is not good. Trust me, it's not good. So we'll come and solve it. But before we solve it, let's go to the next part of the question. This is the next part of the question. By the way, this is 5 marks. By the time you're done with this, it's 5 marks. The next part of the question says that find the percentage or the proportion of time that a customer has to wait. This one is cool. What is it asking you? Which formula is it asking you? Is it asking you for the P dot, PN, L, LQ, W, WQ, U, or I? What formula is it asking you? Find a proportion of time that a customer has to wait. Great answer. Great answer. I like concept bank. So the proportion of time the customer has to wait because the server is being utilized. So this is a utilization. Okay, and this is equal to U, the lambda over mu. So you are finding the lambda over mu. The lambda was already found to be 10. Okay. The mu was found to be 12. You know this from the previous. So you divide 10 by 12, and that will give you the proportion of time a customer has to wait. What did you get? I'll give you a proportion of time a customer has to wait. Get your answer in 2 decimals and then multiply it by 100%. What is it? 83%? Okay. 83%. Please, you cannot convert that 2 minutes to 2 seconds. You can't do that. And the reason why is because 25.2 minutes is not 25 minutes, 2 seconds. Okay, because you got to convert that to, to 60, not in tens, to 60 before you now know its actual value in seconds. So there's no need to really bring seconds into the picture, even if it's a decimal. Otherwise, it will confuse you. Okay, so that's why we didn't do that. Okay, so you get 83%. Okay, I want to believe that the guy who said 83% was okay. I hope the rest of you got 83%. Did you get that? Did you all get 83%? I want to believe that you all got that. Okay, perfect. So that is the answer to this question. Okay, find the proportion of time. So the proportion of time a customer has to wait is 83%. Okay, that's what I mean. The 17% of the time, the server is idle. 17% of the time, the server is idle. All right. Now let's go back to our 25 minutes. Our 25 minutes to 25.2 minutes indicates clearly that so much hours are being spent in the queue. So look at the rest of the question. The rest of the question says this. Management, and this is practical question, deep question. Management perceives that the waiting time you computed in A above, the 25.2 minutes, is not acceptable. And management is faced with 2 options. Option 1, management can employ an assistant for the cashier, or they can open a second cash machine. Okay, they can employ an assistant, okay, or they can open a second cash machine. Which one should they go for? An assistant or a second cash machine? But there are some rules of engagement here. It says that the former, which one is the former? Employing an employee and a cashier. The former, if implemented, will enable, this is cool, 4 requests to be served. So he's giving you a new service rate. It will enable 4 requests to be served every 15 minutes. So he didn't tell you what it would do to the arrival rate. He's rather telling you what it would do to the service rate, which means that the arrival rate will remain the same, because remember, we are talking about the former, and the former is what? Is an employee. An employee affects, a new employee affects the service rate. It doesn't affect the arrival rate. It's a service that will increase, which is good. And apart from that, in 15 minutes, the assistant will receive a monthly salary of 160 cedis. So the assistant is going to get some money. So there's another cost to it, because you don't just employ a new cashier without paying the person. So there's a cost involved. The latter, which is the second option of the machine, this machine option, the latter, if implemented, will improve the arrival rate, okay, to 1 customer every 12 minutes. Now remember, previously, that arrival rate, let me just go back here. Previously, that arrival rate was 2 customers every 12 minutes. 2 customers every 12 minutes, which means it was 1 customer every 6 minutes. Now, we are told that it will lead to 1 customer every 12 minutes. So what it means is that we have been able to reduce the arrival rate, which is good. Remember, somebody was asking why the arrival rate to reduce. We've been able to reduce it because by instituting the machine, the arrival rate has come down from 2 to 1. Yeah. Okay, now let's look at each situation. However, this is the second option. The second option requires, because it's a machine, it requires an initial capital outlay of 3,000 cedis. So the machine will have to be installed near the bank or something. And the cashier who will man the machine, in case of any problem with the machine, that guy was going to receive 250 cedis. Okay. So keep that in mind. We'll come back and analyze each one of them. This is the most important sentence here. The shop avoids a loss. The shop avoids a loss in sales. A loss that they would have, in other words, if they have not instituted any of these two measures, by instituting any of these labor-intensive and capital-intensive measures, they avoid a loss of 80 cedis every month for each minute. Each minute that an average customer waiting time is reduced. So anytime you reduce the 25.2 minutes by 1, you are gaining 80 cedis. If you reduce it by another 1, you are gaining another 80 cedis. You're reducing it by another 1. So each time you're reducing it, that's what happens. Your question is, calculate the financial gain to the ShopRite under option 1, not compare it with option 2. Under option 1 and advice management. Then you calculate the same thing under option 2 and then also advice management, given that the initial capital outlay is sunk cost, and then finally compare the two. So let's go back and take them one by one. What do you think is the first thing we got to do here? The first thing we got to do is to find the new waiting time under these two scenarios. So let's go to the first waiting time. Okay, I'm going to go back here. Watch it. I'm going to put them kind of in the table form. Okay. And then we advise and come to the first person. It says that management employs a cashier or a machine. Let's go to the cashier. If you choose a cashier, 4 requests are served every 15 minutes. So let's go to our board. Okay. I'm going to create a kind of a table. And in this table, I'm going to have something like cashier here, and then a machine there. Okay. So in this one, 4 requests every 15 minutes. That's what it says. And we are talking about service because it's a cashier. So mu, previously the mu was what? It was 12. Okay. Let me just put it on top of it. Previously, let's call it the mu 1. The mu 1 was 12. And now we are told that the mu, let's call it mu 2. The mu 2 is going to be different because it's now 4 requests every 15 minutes. So if you have 4, yeah, I'll wipe this thing up very soon. If you have 4 every 15 minutes, then how many every 60 minutes? If you multiply the 15 by 4, you get 60. If you multiply the 4 by 4, you get 16. Okay. I thought somebody gave me the answer already. Okay. So that is 16. So now we have mu is 16. But don't forget that the lambda will not change because it at the first condition, only the service rate is affected. So the lambda still remains at 10. It hasn't changed. So at this stage, let's calculate the new queuing time under option 2. The new queuing time is going to be the lambda divided by, and we know this already, but let me write it. Lambda divided by mu into bracket, mu minus lambda. Okay. The lambda hasn't changed, it's still 10 divided by mu. Mu has changed to 16, to bracket 16 is 10. When you do that, what will be your value? Who is working with me and tell me? Again, when you convert it to 2 decimal place, first of all, you're going to get 0.1042. Is that it? Okay. You get 0.1042. 1042. You can check, and that's approximately 0.10. Okay. Hours. If you want to get to this 0.10 hours in minutes, what do you get? Like those of you who are working at it, you get 6 minutes. So if you multiply it by 60, that gives you 6 minutes. So the scenario 1 has reduced the 25 minutes to 6 minutes. Keep that in mind. We've been able to cut down the waiting time by introducing a new cashier. What if we had used a machine? So let's go to the machine level. Okay. In the machine section, we were told specifically how that one also works. Okay. So let me just take you back a little. In the machine, we were told that the latter, if implemented, would improve the arrival rate, not the service rate. It will improve the arrival rate to 1 customer every 12 minutes. Remember, it was 2 customers every 12 minutes. Okay. So let's go back and calculate that. So we go back to this thing. It's the lambda 1 was 10. So lambda 2 will be what? Lambda 2 is going to be, remember, it is 1 customer every 12 minutes. So how many customers every 60 minutes? To be 12 divided by 60? 60 divided by 12, sorry. What is that? Somebody has got it. Is it 5? Can you all confirm if it's 5? Okay, good. It's 5. So you can see that the lambda has reduced, which is exactly what we wanted. So previously, remember, the service has increased 12 to 16, lambda has reduced. Now at this stage, the service will remain the same. Okay, the service has still not changed at is 12 original. So keep the service as it is. Let's calculate the new waiting time under this scenario, machine scenario. What will be the new waiting time? This is what's going to happen. Watch this. You have to now substitute the value of lambda over mu minus lambda. And that is going to be, the new lambda is 5 over 12 minus 5. What value do you get? What value are you going to get? And again, you just have to be walking along with me. If you do that correctly, you should get something like 12, 3.6, then multiply it by 60. Some of you are giving me. When you do that, you're going to get 0.0595, which will lead to an approximate value of 0.06. 0.06 hours, which when you multiply by 60, I think you get 0.0596 or so. 595, 0.0595, which is 0.06, which when you multiply by 60, you get 3.6 minutes. I just want to be sure that you guys are with me. You get 3.6 minutes? Let me see some of you while you're saying. Good. So this is it. So you can see that the machine has reduced the hours, the minutes from 25.2 up down to 3.6 minutes. Oh, machine, capital intensive and labor intensive. Which one is good? Well, let's hold on. At this stage, we go back to the story because the thing is that each one has a cost involved. So first, we need to calculate the time saved in each case. Let's try that first. I'll have to calculate the time saved. So the time saved under the first scenario, let's look at the first scenario. The first scenario, if I call time saved, the time saved will be the 25 that you have, 0.2 minus the 6 minutes. Find the answer. And then here, the time saved will be 25.2 minus 3.6. So what is the time saved for the first one? Work it out. What is the time saved? What is the time saved? Is it 19.2? Good. Some of you are right here with me. And calculate the second one. So you get 19.2 minutes. That's the time saved. And this second one, what do you get? Let me see some of you. I'm taking your answers. 21.6. Very good. So you have saved 21.6. So you've saved a lot of time, but we need to convert that time into money. So let's go to the first scenario, monetary gain. What to be the monetary gain here? Now remember that we were told that for each minute that you save, it is converted to some amount of money. Do you remember? You can type the money if you are listening. Okay. Each time you save 1 minute, it is equivalent to how much in cities? Let me see whether somebody is. Excellent, Samuel. Okay. It's equivalent to 80 cities. So we have saved 19.2 minutes here. We multiply that by 80 to get the monetary gain of the time saved. And the same thing we got to do with the second one. So the monetary gain will be the time saved, which is 21.6 times, this is 80, times 80. Okay. 21.6 times 80. So both of them are multiplied by 80. What would the first one give you? One. Okay, so I'm looking for great answers. 1536. Okay, that's what you guys said. So I'm writing that. 1536 here. And then the second one, what do you get? The second one, 1728. Guys, that's what you guys are saying. 1728. I just hope that the rest are confirming that. 1536, then 26, 1728. Very good, super. Now let's go to the question and look at the clauses that were given. We're giving some clauses here. It says that calculate the financial gain, but before that, however, let's go to the first one. It says that the assistant, that's the first request, the assistant will receive a salary of 160. It says a monthly salary of 160. And that monthly salary, everything here is in monthly. Okay, so you don't have to convert anything. 160. So whatever money you had in the first scenario, you got to take that 160 from it. Okay. So let's go down here. What we are going to have now is no longer the monetary gain, but the net gain. So the net gain is going to be the 1536 minus the 160. Let us know that. And here to be, the net gain will be 1728 minus what? Because that one too, there was a cost associated. So you get 1376. Okay, let me write it. That's what you said, 1376. Let's go to the next guy. The next guy, going for the machine. I quite remember he said that if you go for the machine, watch it here. Okay. The cashier who will man the cash machine in case there's a problem will get 250. 250 is going to take that, labor cost as well. So let's go and take the labor cost from that second scenario. This is always how it is. So that will be 250. And what will you get? Some of you have already calculated, and 1478. Oh, I love that. So you get 1478. This is the monetary gain in both cases. Now let's go back to the question. I love this. This is a whole 25 marks, by the way. It says that, however, the second situation requires an initial capital outlay of 3,000 and the cashier who will man the machine. So we'll come back to that. Okay, the shop avoids a loss. And so we've already handled this. Okay, that's what they gain. They cut down each minute. Now, the first B part of the question says, calculate the financial gain to the owner, to ShopRite, under option 1. Now, you didn't say compare it. It says just calculate it on option 1. So let's go to under option 1 and advise the management. Okay, they're just going to do that and advisement. So under option 1, if you look at it here, okay, those of you who have been following me up to now, if you look at the value here, 1378, option 1, what would you say? Would you say that the ShopRite should go for, should undertake this option? And the answer is yes. We just calculated. The reason why you got to say yes. Okay, the reason why you got to say yes is because it gives a positive financial gain. That's the reason. So on its own, without comparing, on its own, you will take this option because it gives a positive financial gain. Positive financial gain. On the second scenario, on its own, you go for it because it also gives what? A positive financial gain. Okay. Now let's go to the second scenario because there was some clauses there. So this is the first scenario. We've done that already. Advise the management on this option. Management can choose this option because it gives you a positive gain. Okay. Now look at the second scenario. Say calculate the financial gain to the ShopRite under option 2, assuming, this is a key point there, assuming the initial capital outlay is sunk cost. What does it mean when we say an initial capital outlay is sunk cost? What is a sunk cost? What is a sunk cost? Who can tell me? I mean, if you know, those of you in accounting or finance, you should be able to know sunk cost. Okay. What is sunk cost? Clementine, what is sunk cost?
Doc, a sunk cost is a cost incurred whether or not production has taken place.
It's a cost incurred whether or not production has taken place. Very good. I see no other hand is up. Okay, so we'll buy that. But here's the key thing: it is irrecoverable. Okay, it's sunk. Okay, it's irrecoverable cost. So if we assume that the initial capital outlay is sunk cost, it means that we are not considering it. It's sunk. We're not considering it as part of our cost because, you know, whether you do whatever is not going to affect. So what he's trying to say is that do not incorporate that into your final net gain when you are now coming with the conclusion. Do not incorporate that. So now we are going to make our decision without considering that. So that is why when you go to the second scenario, you will see that you can make your decision and say that, okay, don't let us consider the 3,000. On its own now, this value of 1478 shows that there's a positive gain. So you will advise management to consider this. That's all. Now let's go to the third part. And this is a beautiful part. Assuming now the initial capital outlay, okay, that's all we did. Assuming the initial capital outlay is sunk, okay, so now this is where you got to compare it. Assuming the initial capital outlay is sunk cost, still assuming that is sunk cost. In other words, don't incorporate that 3,000 original. Which of the two options would you recommend to management? I need an answer. Okay. Which now of the two options would you recommend to management and why? Should the management go for the labor intensive option or they go for the capital intensive option? Eric says option 2. And your reason is what? Your reason, I just need a simple reason. What is your reason? I need a simple, you will tell us. Who is there? Actor Wilson is gone off the radar. And Sika is also gone off the radar. These are the people who are, okay. Yes, Deborah, that's a good answer. It has a higher net gain. I love that answer. Bishop, high financial gain. I agree with that. Okay, okay, good. Excellent answers. So the reason is because it gives you a higher net gain. That's all. And that is why comparing the two, assuming that the initial capital outlay is a free gift. If you look at past questions, it's a free gift from, a service company. Then this option is the one to go, capital intensive option, option 2. Now let's go to the latter part of the question. The latter part of the question says, after how many months, this key, after how many months would management be different between the two options? Look at the question. After how many months would management be different between the two options? Now, what do we mean by being different? It means that whatever option A, okay, but whatever option 1 is giving you will be equal to whatever option 2 is giving you. That's when you are indifferent. Take note. Whatever option 1 is giving you is the same as whatever option 2 is giving. That is why you become indifferent. But they are all giving you the same thing. It means that what the values are the same. But we are talking about how many months. So how many months here will mean that now you got to consider the initial capital outlay for the option 2. Because as you bring in the option, that is when the initial capital outlay, because normally you got to take some time before the initial capital outlay manifests itself. Because before you can recoup the initial capital outlay. So since the timing has been brought into question, you got to consider the situation. So how do you do that? Write the value of the option. Now we don't know how many months. So we're going to represent that how many months by X. So we take the value of option 1. Do you remember the value? The value of option 1 was 1,003. What's that? I forgot. 1,376. Okay. So that is 1,376. Good. Oh. Okay. So option 1 is 1,376. Is it 76 or 78? Come on, somebody should write it down. 1,376. Okay, good. 1,376, but we don't know how many months, so we represent the months by X. And this should be equal to option 2, and option 2 was 1,478 X. We don't know the month. But I remember that option 2 will capture the initial capital cost. So let's take out the initial capital outlay, which was 3,000. That's it. And then now we can find how many months it would take for the two to be equal. Now, please remember, whatever answer you get, you can double check to be sure that they are truly the correct answer. So let's find the value of X. At this stage, you group items. So you can move the 3,000 to the left and then move this one here. So that will give you positive 3,000 equal to 1478X minus 1376X. 1478X minus 1376X, what value do you get? 14.7 minus 13, what value do you get? I need a value first. Okay. So you're going to get 3,000 equal to that value. And that value will have an X attached to it, 102X. Good. So you get 102X. Divide both sides by 102, this side by 102. So X is going to be equal to 29.41. Okay. So you're going to have 29.41 months. That's what it means. So what does this mean? It means that it is after 29.41 months before the two will be equal. Now, in order to be sure that that 29.41 is true, come back and substitute that 29.41 into the first equation, wherever you see x. Okay, so you come and substitute that here, and you substitute that here, and you will check the two. You see that they will be equal. Okay, so if you like, multiply 1376. What do you get? 1376 times 29.41. Okay, and then you put it down, and then you multiply 1478 times 29.41. Then the second one, you subtract 3,000 from it. Whatever value you get, it will be the same. You can check it. I did it, and you can check it. And when you do, that will tell you that your 29.41 is correct. So that is 29 months, 0.41 before the initial capital, before the two options, you will be indifferent, meaning the two will, you will not have a choice as to which one to choose. You will not have a choice of the, because they are all giving you the same net returns. That is how we calculate this. And again, you can go through this again with other things. See, here's the thing. Let me just give you everything, by the way, is in the slides. You should go and work it out and see. Okay. All the things that we've done, they are all here. Okay. And this is the final one that we did. Okay. That is how long it will take to recoup the initial cost. You can go and work yourself on this. But a key point I want you to note here is that sometimes more is saved. You can see that here, the capital one, the capital intensive one was the choice. But sometimes more is saved if you hire an employee than if you go for the machine. As a manager, what you got to notice is that both are still better than the original one. 25 minutes was still higher time waste. But the 6 minutes was better, and the 3.6 minutes was also better. But in reality, it's hard to choose between the two, to be honest with you. With 6 minutes and 3.6 minutes, hard. Why? Because there are other factors involved. We didn't take care of idle time, where the customers idle at some point in time, the loss of space. People come, they don't have space, people are just delaying, they are cleaning their face, they are doing makeup, and things like that. All of these things are not calculated. So in reality, there are a lot of factors that are involved. So in a practical situation, you got to take into consideration all of these factors. But here's the key point that you got to know. Queuing model helps you to decide. It doesn't decide for you. It helps you to detect the cost trade-off, when it comes to improved service. So you have to make sense of the final, situation. Here's a typical example that you should work on your own. Accounts officer at Royal Bank registers all customers. The customers desiring to open accounts arrive at a rate of 2 every 13 minutes. And the account officer spends an average of 12 minutes with each customer setting up the account. What is the average time? The probability that no customer is waiting, the average number of customers in the queuing system. Find the average number of customers in the waiting line, the probability that the server is busy. Now, the manager is thinking of two alternatives: employ an assistant, okay, or use an electronic machine. The first option will lead to that, the second option will lead to that, and again, the same situation, and then after how many months? So familiarize yourself with these examples, and you will know how best to execute queuing model. Ladies and gentlemen, that brings us to the end of the entire caboodle. What a joy. What a joy to have an unbelievably wonderful time like this.